Hi everybody, my name is Johannes and I'm happy to present our paper Counting with Bounded Treewidth, Meta-Algorithm and Runtime Guarantees. And this is joint work with Markus from Vienna. Okay, let's start with the motivation. There's been increasing interest in solving various model counting problems over the last few years. The propositional model counting problem, or also known as number set or subset, is the canonical problem for the complexity class Sharpie by results from Valiant in the late 70s. In fact, already the propositional model counting problem has various applications. However, in practice we often introduce auxiliary variables when encoding, so we're then only interested in the count with respect to those variables. In this question is the projected model counting problem, or in a slightly more general setting, the projected solution count. For the question we've given an input and a projection set, and we ask to compute the projected model count, which is the number of solutions that were intersected with the projection set. The problem is known to be one level higher in the counting hierarchy, and for set we have sharp dot NP completeness. An approach to still solve the problem is to apply ideas from parameterized algorithmics, meaning that the instance has a certain structure which we can exploit by an algorithm. And one such parameter is the Treewidth, and that's what we're considering here. Actually, there have already been a couple of results on the complexity of projection and counting when parameterized with Treewidth. So in terms of upper bounds and specialized dynamic programming algorithms. Recent results shared conditional lower bounds, establishing that we cannot do better, assuming that we believe the exponential time hypothesis. So that's it then, right? Well, not exactly. Recent implementations exploit this parameter in a practical setting, and some of those implementations are even in a very general way implemented. Since the implementations are competitive, the immediate question is, can we go beyond those specialized dynamic programming algorithms? So our research questions here are as follows. Can we extend an arbitrary dynamic programming algorithm for counting projected solutions? What properties do we need for such algorithms? And can we specify it in such a way that we actually have a meta algorithm that runs on existing algorithms? If you have better things to do on a Sunday late afternoon, well, the short version of our contribution is, yes, we have a way to actually extend dynamic programming algorithms. The runtime increases by 1 exponent in the Treewidth, and we illustrate our results for quantified Boolean formulas. As a corollary, we obtain projected solution counting algorithms for a variety of problems ranging from graph algorithmics to logic programming and reasoning. Let's quickly fix a few things on the theoretical background here. Let's have a look on Treewidth first. Treewidth is a combinatorial invariant that has various applications in different areas such as Bayesian reasoning, constraint satisfaction problems, and various graph problems, and it actually renders many problems that are computationally hard tractable. And in graph theory, the easiest way to understand Treewidth is to see it as a measure that allows us to capture how tree-like a graph is, because many problems are hard on graphs but simple on trees. And Treewidth is defined in terms of tree decompositions. And a tree decomposition of a graph, such as the one on the left-hand side here, which consists of the vertices A, B, C, Y, and X, and a couple of edges between those vertices, consists of a tree where each node is attributed with a subset of the vertices of the original graph. Intuitively, the tree decomposition later gives us an evaluation ordering and specifies which of the vertices we have to consider together when evaluating the graph in parts for our actual graph problem. In order to make this work, the tree decomposition needs to have a couple of properties. The first one specifies that we don't forget any vertex, meaning that each vertex of the original graph occurs somewhere in the back. Next property specifies that we don't forget any edge, meaning that the two endpoints of each edge occur at least in one bag together. And now quickly go over each edge of our graph and see that this is actually the case for the decomposition on the right hand side. And the last condition, which is known as the connectedness condition, states that for each vertex of the graph, that whenever it occurs in two bags of the tree decomposition, then it occurs in every bag between those two nodes. The connectedness condition essentially ensures monotonicity in the evaluation and makes sure that we don't have to do any backtracking in the end for the standard algorithms. The example, you can see it for the vertex B, here for the vertex C. Then the width of a tree decomposition is the size of its largest bag minus 1 for some arbitrary technical reasons. And the treewidth is the width, so the smallest width, over all possible tree decompositions of the graph. Now let's quickly have a look on how we can use tree decompositions to solve a combinatorial hard problem faster. Consider our graph from before on the left hand side. First we decompose this graph into a tree decomposition, and here you simply have to trust me that this is actually a valid tree decomposition of the graph above. Then we traverse the tree decomposition, usually from bottom up, so from the leaves to the root. And at each node we run a local algorithm that has only a local view on the graph. Our node here that consists of the vertices B, X, and A, we can see in the graph only A, X, and B for the local algorithm. And then the algorithm usually stores values for B, X, and A in a table. For set, the trivial way is essentially to store all the potential truth assignments for the variables B, X, and A here. Proceed with B, X, and C, and again we store information for B, X, and C, but we have only a local view on B, C, and X in our graph. And on top of the satisfiability for this local part of the graph, so for our actual graph question, so graph problem, we have to incorporate the information from the table that we've computed before. We proceed above, and essentially we just go along the tree decomposition. At the root of the tree decomposition, the table essentially contains only records that satisfy all the properties that we need for our graph problem. And this one can usually show by establishing invariants for the local algorithm and doing simple structural induction proofs. In the end, at the root, we take the results for the table at the root and combine this to the solution of the overall problem for the entire graph. If we keep the tables during our traversal, we can reconstruct the solutions by doing the opposite direction. However, for the counting question or the decision question, it's usually enough to have the information at the root table. How can we solve projected solution counting? By using tree decompositions. While this sounds super general, let me take a step back and explain this for the satisfiability problem. Take a look on the following instance, which is a CNF formula, and we use an algorithm given by Sama and Sider from 2010. You can easily spot, I guess, just joking, that the models of this formula are the following. So B, AB, BC, and so forth. This graph representation, the primal graph, which has the variables as vertices and places a clique on all the variables that occur together in one class. Decompose the graph accordingly, and surprise, well, it fits in our example. Again, traverse the tree decomposition. Assume that we start from the leaf, so where we see B, X, and A together in one bag. And in the graph, we can see A, X, and B together and their relationship. Take as local formula all clauses for which the variables that occur in the clause are a subset of the variables of the back. So in our case, we only have those two clauses here. We simply store in a table all the assignments for A, B, and X that satisfy the subformula. Proceed with the next back and the next subformula. Consider the satisfying assignments and incorporate the information from before, meaning that we store only assignments which can be extended from below. We forget a variable and the assignments fall together. Same thing happens for the next leaf. Again, we forget a variable. We combine the matching truth assignments from both sides, meaning that we take a natural join. At the root, if we have an entry in the table, we know that the formula is satisfiable. And we can also go back and construct a satisfying truth assignment. It can be naturally extended to counting by simply storing counters. And the counter just states to how many solutions we can extend the row at the node if we just go in the opposite direction and traverse backwards. For propositional counting, the runtime is single exponential in the Treewidth. I explained to you that we can trivially extend this algorithm to model counting. Then the question is, can we also extend this to projected solution counting by simply adding an additional counter? And unfortunately, the answer is no, unless the exponential time hypothesis fails. There is no algorithm for projected solution counting that runs in time double exponential. This is the case for such, but does it eventually get simpler? Maybe the special case is just weird. So what's the general case? Well, we consider projected solution counting for QBFs. Fortunately, the answer is no, unless the exponential time hypothesis fails. And we always need one exponent more for projected counting. Still, we can construct an algorithm, right? Repeating the projected solution count, however, is too expensive. What we will do is that we compute the numbers locally, and we will still use the old algorithm but extend this. Projected solution counting runs in 3 steps. First, we run the algorithm, so the original algorithm, keep the tables and remove all rows that do not lead to a solution in the end at the row. On top, we run a meta-algorithm for projected counting, and this is the contribution of this paper here. In order to achieve this, we need to assign counters to a set of rows. Effectively, this has certain connections to what is known as subtractive reductions in complexity theory and the principle of inclusion and exclusion in combinatorics. The ingredients for our algorithm. We need to define an equivalence class, so a partition of the tables of the rows. The subsets of resulting row clauses to a counter, and then we maintain the counters using the principle of inclusion and exclusion. Let's have a look on a very simple example and consider as projection variables x, y, and z. Say in our table at t, the variable x is set to 0, 1. We only have other variables that do not occur in the projection set. Similar below. What would essentially happen is that we overcount, as we're actually only interested in the count with respect to x. So we introduce counters that represent the inclusion-exclusion principle. What does this mean? Well, we have the counts as before, in our example 1, 3, and 2. If we sum this up, this is clearly too much, in our case 6. Also store counters for the overlapping case, meaning what's the count when the first and the second row overlaps, here for example 1, when the second and the third row overlaps, here 2, and when the first and the third row overlaps, so here 1. In total that would be 4, and we have to subtract because we overcounted here. However, by simply subtracting the overlapping ones for 2 rows, so 1, 2, 2, 3, 1, 3, etc., we would reduce the count too much. Hence again we have to add a counter that represents 1, 2, and 3 counts. In our case 1. In the end, the projected model count at node t would be 3. Approach is known as principle of inclusion and exclusion in mathematical combinatorics, which allows us not just to count the number of elements in the union of two finite sets, but extend this to 3 sets, or even more general, to a family of finite sets. That's what the projected model count is. In order to do the computation, we in addition need the intersection projected model count, which allows us to reconstruct the projected model count in the end. What our local algorithm essentially does, it only stores the counters, so the IPMC values. The PMC values are used immediately. Slightly modify the principle of inclusion and exclusion by, instead of storing the cardinalities, we rely on the stored IPMC values. Let's have a look on an actual example. Take the formula from earlier and assume that the projection variables are x and y. Consider the models from before and intersect each set with x and y. Then we end up with 3 distinct sets. How do we use dynamic programming to solve the question and avoid enumerating all solutions? Start as before and run the algorithm that solves the decision problem. Then we clean up the tables and remove all entries that do not provide a solution in the end, or more precisely, that cannot be extended to a valid solution of the problem. Note that the tables are effectively a compact representation of all potential solutions. Look on the back that consists of B, X, and A. The satisfying truth assignments as before, and the assignment 1, 0, 1, so the one that sets B to 1, X to 0, A to 0, represents one solution. Assignment 1, 0, 1 also represents one solution to the subproblem. Or if we restrict this to X, one row is overlapping. When we consider the back BXC and the according subproblem, we have the satisfying assignment 1, 0, 0 for the local formula that extends a previous solution, so where we also consider the A with a count of 1. For the next row, and again we only have one intersecting row. However, when we forget X at a node, meaning that previously we were able to set X to 0 and 1, meaning that we would have 2 solutions. We simply add values. For the next one, we have to combine it accordingly. Proceed along the tree decomposition. Combine the values for join nodes. The root, we're in the position to compute the projected model count for the overall problem by summing up the values that represent no overlappings, subtracting the overlappings, etc. And in our case, we have 2 plus 2 minus 1 equals the total number 3. Just as a side mark, we can immediately solve the corresponding validity question for QBF, because we obtain as result 3, whereas for validity we would need 4. For QBF, we're simply one level up QBF, and the other problems we increase by 1 exponent. And we show that you can use our meta algorithm if the following properties are satisfied. First, you need to have compatible solutions, essentially a monotonicity property among the back relations, meaning that's forbidden if table records differ or change decisions at some decent node for parts of the solution. And the algorithm has to be complete. Then you can use a decision algorithm and apply our meta algorithm on top in order to solve projected counting. Let me quickly sum up. Consider the structural parameter Treewidth in a very general setting and specified a meta algorithm as well as very general conditions. Decision algorithm for a problem has to satisfy in order to use our meta algorithm for projected solution counting. I believe that this can be very interesting, in particular as recent results showed promising applications and compatibility with state-of-the-art model counters and projected model counters, and in connection with the system DPDB that allows for easy implementation of dynamic programming algorithms. One might use this to solve a variety of problems, even in practice. From the theoretical perspective, PSC is not only believed to be harder in the classical setting, but assuming EDH, we require 1 exponent more in the Treewidth for the runtime. Here we provide a meta-algorithm that one can use on top of decision algorithms that were originally only designed for really just the decision problem. The established conditions ensure correctness of the algorithm. And since my last name relates to a tree, I have to reassure you that during the preparation of this talk, no living tree was harmed. Thanks to our sponsors, and stay tuned. Hope you have a couple of questions.
Okay, so hello everyone. It's my pleasure to be here today. I'm Nourhan Ehab. I'm a PhD student at the German University in Cairo. And today I'm presenting to you our paper titled Algebraic Foundations for Non-Monotonic Practical Reasoning, which is joint work with my PhD supervisor, Haythem. As the title suggests, we are providing foundations for non-monotonic practical reasoning. And this is why a natural starting point for this talk is for me to outline what exactly do we mean by practical reasoning. In a nutshell, practical reasoning is reasoning about what to do. It is the process of deliberation we undergo whenever we need to choose what to do from a possibly conflicting set of motivations in light of our views. In order to demonstrate the variety of situations that requires us to do practical reasoning, let us consider this example. And this will be my running example throughout this presentation. I will refer to this example as the weekend dilemma. So in this example, Ted needs to decide what to do over the weekend. He has to work on a long overdue presentation. Meanwhile, Ted also had previous plans with his best friend Marshall to go on a hunting trip during the weekend with him. Ted thinks that he can go to the trip and dedicate some time to work on the presentation there. Barney told Ted that he heard from his fiancée Robin that the trip location has no internet connectivity, so Ted will not be able to work on the presentation there. Ted trusts that Robin usually tells the truth, but suspects that Barney might be lying to make him not go on the trip with Marshall. Ted desires to go to the trip, but he feels obliged to desire to not make his boss mad in order to be more responsible. Now the question is, what should Ted do? And the process that Ted will go through in order to decide what exactly should he do, whether to go to the trip and risk not being able to work on the presentation, or just stay and not go to the trip, is what we refer to as practical reasoning. And as you can see, it involves motivational attitudes of Ted. I'm highlighting these motivational attitudes here in this color magenta, in addition to his informational attitudes or his beliefs that I'm highlighting here in blue. So at the end of the day, practical reasoning is a joint process that you have to reason with informational and motivational attitudes. Modeling practical reasoning has attracted a lot of attention in the KR community, giving rise to a lot of theories coming in different flavors. However, we claim that a comprehensive and adequate logical theory remains missing. And finding an adequate theory for practical reasoning becomes very important because we usually think of rational agents as practical reasoners that form intentions to achieve their desires according to their beliefs of the world. So modeling practical reasoning is at the end of the day an adequate way to model rationality. Now, I want to talk about why do we want to model non-monotonic practical reasoning and why is practical reasoning non-monotonic? In practical settings, our agents' beliefs are usually governed by a system of preferences. They are continuously being revised, and this is a side effect of the natural incomplete knowledge about the world. And since the agent's intentions are usually dependent on the beliefs, then the revision of the beliefs must be reflected on the agent's intentions. There are a lot of approaches in the literature that models preferences among the different mental attitudes. There are other theories that model joint belief and intention revision, but there isn't one theory that accommodates both. And this is why our main objective in this work is to introduce general algebraic foundations for first-person practical reasoning, where we can do both. We can model preferences among the several mental attitudes, and at the same time, we want to model the joint revision across the different mental attitudes. Our second objective, we will be providing precise semantics for an algebraic logic. We will refer to this algebraic logic as log APR, where log stands for logic, A for algebraic, and PR for practical reasoning. And in this logic, we will be able to model the joint reasoning with both graded beliefs and motivations. So this is the outline of this presentation. Since log APR is an algebraic logic, I will start by outlining some algebraic foundations that we will base our syntax and semantics of our logic on. And then I will go ahead and present the syntax and semantics of log APR. Then we'll conclude and present some finalizing remarks. Now, going on to our first part, log APR, as I just said, is an algebraic logic. So my starting step, I want to review what we mean by a Boolean algebra. And a Boolean algebra is a sex tuple that is made up of a set of objects P, two binary operators, these two operators, and a unary operator, in addition to bottom and top, where bottom and top are always subsets of P. The Boolean algebra is closed under the two binary operators and the unary operator, and they observe classical commutativity, associativity, absorption, and complementation properties. We're using Boolean algebras to model reasoning, and this is why we will take our set of propositions, our set of objects to be our propositions. Then we'll take the plus to denote disjunction, the dot to conjunction, and then the minus, we'll take it to be the negation. Another central component of algebras in general is the notion of filters. And the notion of filters lends itself very nicely to our objectives. Let me first outline what do we mean by filters. Now, a filter generated by a set Q, which is a subset of P, denoted f of Q, is Q prime, where Q prime is the smallest set containing Q, and top must be in Q prime. If A and B are Q prime, then A dot B is in Q prime. Then finally, if A is in Q prime and A is less than or equal B, then B is in Q prime as well. We can take the notion of filters to denote in a way a logical consequence of a set of propositions Q. If we take that to be conjunction, and this is a classical order on the propositions that can mean implication. So this is in a way the set of logical consequences of a set of propositions. Now, remember that we're modeling practical reasoning, and practical reasoning usually involves several mental attitudes, several sets of propositions rather than one set. And this is why the very first thing we did in this work is that we generalized the notion of filters into a generalized notion that we will call it multifilters. And what we want to do is we want to generalize filters to handle several sets, and we will take each set to represent a separate mental attitude. Now, just like filters were based on a classical order, we are defining an order, but this time it's on the tuples, since our filter, our multi-filter, is defined on sets. And we're defining a set C to be a subset from 1 to K. Now, our multi-filter, denoted this way, is a tuple of sets, this time from Q1 prime to Qk prime, where each Qi prime is the smallest set containing Qi, and top is in Qi prime for all of the Qi primes. If I is in C and A is in Qi prime and B is in Qi prime, then A dot B will be Qi prime as well. And finally, if we have an order between a tuple from A1 to AK, B1 to BK, and each AI is in the corresponding Qi prime set, then each BI should be in its corresponding Qi prime as well. So if you look at it, this set C first, it just tells us which sets are closed under conjunction. And this is very important to model motivational attitudes in particular, as desires, for example, need not to be closed under conjunction. And then if you look at those three properties, those are just generalizations of the three properties on normal filters. We're just generalizing in order to handle reasoning with more than one set. Now, this was what I wanted to say regarding our algebraic foundations. So what I will do now is I will go ahead and start presenting our language, our logic, log APR. I always said that log APR is an algebraic logic. So first, I want to highlight what exactly do we mean by that. So first of all, log APR is an algebraic sorted logic of graded propositions, where a graded proposition is a proposition associated with ordered grades. And we will take the grades to mean, trust, or preference measures. Log APR is an algebraic in the sense that it contains only terms that are algebraically constructed from function symbols. So even our logical connectives are functions. And both propositions and their grades are introduced as first-class individuals in the ontology. So we can have terms denoting grades, so terms denoting propositions, terms denoting graded propositions and graded propositions in an arbitrary compositional structure. Now I want to present what is log APR theories, how our theories look like in this logic. Our theory is triple, B, M, and R, where B is a set of propositional terms representing the agent's beliefs. We have a set of tuples from M1 to Mk, a K tuple of subsets, where each subset represents a motivation type. And this is a major deviation from the classical BDI approaches, where generalizing desires into a set of motivations as a rational agent might have more than one motivation. We have a set of bridge rules, where each bridge rule is in this form. And what they basically mean, they license the interaction between the different mental attitudes of the agent. So this basically says if B is a subset of the theory, of the set of beliefs in the theory, and M1 to Mk is a subset of the corresponding set of motivations, then we can add B prime to M1 prime to Mk prime to our current mental states. And of course, all of the premises and the consequence are subsets of propositional terms. Having defined log APR theories, now I will go back to my introductory example, the weekend dilemma, and see how can we model this as a log APR theory. First, now let P denote working on the presentation, T denote going to the trip, and M denote the boss is getting mad. Our corresponding log APR theory will look as follows. A set B contains two beliefs. Remember that Ted thought that he can go to the presentation and he can work on the presentation and go to the trip, but he was not very certain. And this is why we're representing this here as a graded belief, and we're assigning this a grade of 5. Then Ted acquired information from a source, a chain of sources from Barney and Robin, that he cannot go to the trip and work on the presentation at the same time. And since this information was obtained from a chain of sources, we are representing this with a grading chain. First, Ted trusts the source of the information with a degree of 10, but he heard this from Barney, and he trusted Barney less, and this is why we're assigning this graded proposition a degree of 2. And this is one utility for modeling the nesting of graded propositions in log APR, to model information acquired from different sources that have different degrees of trust. Our two sets of motivations, I'm taking the first set to denote Ted's desires, and the second set will be taken to represent the obligations. And Ted desired to go to the trip. We're giving this a grade of 1. Ted felt obliged to work on the presentation. Then we had a higher order motivation. He felt obliged to desire to not make his boss mad. And this is one other utility of allowing the nesting of propositions in the motivations. It can represent this sort of higher order motivations. We have a set of bridge rules, which is the set of instances of the following rule schema, where phi and g are variables, And each set in the bridge rules, both in the premises and the consequence, are taken to in the order of the theories that we have. So the first set in the bridge rules, they model beliefs. The second one is the desires. The third one is the obligations. So we can read this bridge rule as follows. If Ted desires, remember that M1 denotes our desires. If Ted desires something, phi, with a grade G, then, if Ted is obliged to desires phi with a degree of G, then he desires the same phi with a degree of G. So we bridge this phi from the set of obligations to the set of beliefs, to the set of desires. The second bridge rule tells us if Ted desires to make his boss not mad with some grade G, then he desires to work on the presentation and he desires to not go to the trip with the same grade. So this is a sort of a desire generation tool. Now, we're ready to, first of all, our propositions are interpreted by a complete non-degenerate Boolean algebra. And I'm showing here how the different syntactic structures of log APR are translated to their semantic counterparts by means of an interpretation function that we have. To represent logical consequence, I will use our notion of multifilters that I presented by the beginning of this presentation. But remember that multifilters was based on an order on the tuples. And this order comes from the theory that we have. So first, before defining logical consequence, I will define what is a T-induced order. And the intuition of this order is that the order of the tuples come from the bridge rules. So whenever we have a bridge rule that looks like this, then the interpretation of each set, we have an order that looks like this. The interpretation of each set in the premises is less than or equal the interpretation of each set in the consequence. And now to define logical consequence, a T-induced multifilter, denoted this way, is the T-induced multifilter is a tuple of sets, and this tuple of sets will be M1 to Mk. And then for every propositional term phi, we will say that it's a belief consequence if the interpretation of phi is in the set B of the multifilter induced by T. And it is a motivation consequence if the interpretation is in some set of motivations in the corresponding T-induced multifilter. So now we have a definition of logical consequence for a generic set of attitudes, we want to use multifilters in order to reason with different sets of attitudes. Now, remember that our theories had graded propositions, and unfortunately, this definition of logical consequence is not enough to address graded propositions. And in order to see that, I go back to my log APR theory. This is what we had. And then I will be showing the agent's beliefs to the top of the circle. Those are the desires, and those are the obligations. And then to make things easier, those are the bridge rules that we had in the example. If we come to compute the multifilter, we will get things like the classical logical consequences in the set of beliefs. We will get the consequences of the bridge rules, but you can see here that neither bridge rules can be fired. Both of the premises are not there in our three sets. And this is why getting the classical multifilter is not enough here to address these graded propositions. And it makes sense, for example, if Ted believes that he can work on the presentation while being on the trip with some grade, but he's not very certain about it, that he can get it as a logical consequence if he does not believe its negation. And this is exactly what we will do. We will start admitting to our set of propositions that are not in the original theory, but they are graded in the original theory, or follow from graded propositions in the original theory. And this is why we will extend our notion of multifilters to a more liberal notion into what we will call graded multifilters in order to address those graded propositions. And then since we're allowing the nesting of graded propositions, then those graded multifilters will come in degrees, where each degree, where each level will correspond to accepting nested propositions at a new nesting level. So let me start by doing that. Let's see how the graded multifilter at level 1 will look like. First of all, we'll get this embedded graded proposition, and this embedded graded proposition had a grade of 2. Then we'll get the other graded proposition in the beliefs. It has a grade of 5. And then we'll get the classical consequences of the graded propositions that we currently have. So we will get P and T as classical consequences of P and T. We will do the same thing with the desires and the obligations, extract all of the embedded graded propositions at level 1, and now we are ready to apply the bridge rules. This first bridge rules fires the rule that tells us if we desire something in the set of obligations, then we desire it. So this desire will make it to the set of desires. And then the second bridge rule fires, and it will make us add those 2 consequences to our set of desires as well. And this makes up our graded filter at the first level. And we don't have any contradictions here. Kat believes that he can go to the presentation, he can go to the trip and work on the presentation. He desires to go to the trip, and he's obliged to work on the presentation. Now, going to the next level, we will extract the graded propositions at the second level. Now, P if and only if not T was nested at 2 levels, and now it's graded by a grading chain that has 2 grades, 10 and 2. So what we will do is we will define a fusion operator in order to get a grade for P if and only if not. I'm taking here this fusion operator to be the averaging operator. So P if and only if not T gets a grade of 6. And then all of these nested propositions, they will be extracted out with their grades. But now, if you look at it, we have a contradiction. We have P if and only if not T and P and T in the beliefs. We have P if and only if not T, and Ted desires to go to the trip, he's obliged to work on the presentation. So the second level graded multifilter is contradictory, and we must make sure that we get rid of these contradictions. To do that, we generalize the notion of kernels, Hansen's kernels, and we define it to be a tuple of sets rather than one set, where if we get the multifilter of this tuple of sets, the union of the sets in the multifilter will be contradictory. And then the contradictions will be resolved according to the agent's character. We're defining a notion of the agent's character. This character will be an ordering over the different sets of attitudes, and it tells us which attitude does the agent prefer to give up propositions from in order to resolve the contradictions. And we will use also the grades of the contradictory propositions in order to resolve the contradictions that we will have. Those are the 4 bottom kernels that we get in this example. We order the kernels according to the character. So let's say in this example, Ted prefers to give up propositions from desires first. So this is the set of desires, then set of obligations. And then finally, he does not prefer to give up propositions from the set of beliefs. And this is why this is the order that we have here. First, desires, then obligations, then beliefs. And then we take the kernels that we compute in order. And in order to resolve the contradictions, we will always pick the leftmost set, because the leftmost set will contain the attitude that we prefer the most to give up propositions from. Now, in this first kernel, we are forced to give up a proposition from the set of beliefs. From these 2 beliefs, P and T had the least grade. It has a grade of 5. And this is why we will choose here to give up P and T from the beliefs. And consequently, P and T will go away as they were consequences of P. Now, if you look at it, we still have a contradiction between the beliefs, desires, and obligations, and even between the desires themselves. And this is why we construct 3 other kernels after we give up P and T from the beliefs. And now we consider the first kernel. Our leftmost set contains the desired T. So this T we are forced to give up. We are forced to give it up. We will give it up from the set of desires. And then we end up giving up P and T from Ted's beliefs and its consequences, and T from the desires in order to preserve the consistency. And there we get a consistent graded multifilter at the second level. Of course, this is not the formal definition of a graded multifilter. I was just presenting it with the example to make its presentation easier. Now, finally, we're presenting graded consequence. And graded consequence, just like we defined logical consequence as membership in the classical filter, we define graded consequence as a membership in the graded multifilter. But remember, those graded multifilters come at a particular level, n. So if this is the graded T-induced multifilter at a particular level, then phi is a graded belief consequence if the interpretation is in the corresponding set of beliefs in the graded multifilter, and it is a motivation consequence if its interpretation is in one of the set of motivations in the graded multifilter at level. Both of these graded consequence relations are non-monotonic, and they reduce to their classical counterparts if the level is equal to 0. So what we did in this work, we introduced general algebraic foundations for reasoning with several mental attitudes. I presented a semantics for a logic that we call log APR that accommodates joint reasoning with graded beliefs and motivations to decide on a consistent set for beliefs and intentions. What we plan to do next, we're currently working on a generalization of log APR to provide a general framework for reasoning with a generic set of graded mental attitudes to include other mental attitudes such as doubts or fears or regrets in order to model a more humane logical agent, so to say. And then we will be developing the proof theory for this generalized framework of reasoning with several graded mental states. Thank you very much for your attention. If you have any question, I will be happy now to answer them.